Okay, we're on lesson 10.1.1, Introduction to Chords. So for chapter 10, we're spending a bit of time on circles and a lot of the different details of circle, little parts of them, and how to find the important information that we need based on these little parts of it. Okay, so we're gonna take a minute here. Well, you take a minute here to read the problem, the backstory of this baobab tree that is found in Africa, Australia. Okay, all right. Okay, in part A, this arc AB represents the curvature of the tree fragment. Trace this arc as neatly as possible on tracing paper. Decide how to fold the tracing paper to find the center of the tree. So you take your tracing paper over your arc, trace it as neatly as possible. So here's A, all right, and again, make sure you trace over. This is your B. All right, so here are my tracing paper. So how do I find the center of a circle? What you want to do is you want to fold the arc so that it overlaps itself, but it doesn't have to be completely halfway. It could be if you want to, but as long as you are touching the arc somehow. So notice how you can see I'm way past the A, right? A and B are not matching up perfectly, so I'm way past the A, and that's okay. As long as the arc is on itself, crease that down, okay? Open up. Do it again, but now a different spot. So maybe make the A match the B better. So ooh, I'm pretty much on the B. Okay, trace that over. Okay, trace that over. And then maybe do another one, right? Maybe do a B above the A. So it doesn't matter how many you do. The more you do, the more accuracy you have. Right, again, as long as the arcs are on top of itself, you can crease it down. It's a little hard because I already have some creases here. All right, so crease it down, but those lines should all intersect at one spot, and that is the center of your circle. Okay, so then if you continue reading your problem, it says in part A, you locate the center of the circle. So that's my center. I'm moving that C. Use a ruler to measure the radius of that circle. If 1 centimeter represents 10 feet of tree, find the approximate length of a radius and diameter of a tree. Does the tree appear to be longer than 45 feet in diameter? All right, so this is my circle. This is my radius. How long is my radius? So pick any one of these. I measured about 2.3 centimeters. All right, so 2.3 centimeters. 2.3 centimeters. So if 1 equals 10 feet, then 2.3 times 10 is 23 feet of radius, right? So that's your radius. If you double that, you get 46 feet to be your diameter. So is the tree longer than 45 feet in diameter? The answer is yes. So that is a perfect way to figure out part B. Okay, moving on to number 2 here. It says parts of a circle, part 1. A line segment that connects the endpoint of an arc is called a chord. So from one end of the arc to the other end of the arc, like so, if you connect it, that's called a chord, right? Because it doesn't go through the center of a circle. If it goes through a center of a circle, it's something else. So a chord is kind of like a incomplete diameter. It doesn't go all the way from one end to another, right? It just connects 2 sides. So this is called a chord, okay? Thus, AB and diagram below is an example of a chord. So here's a AB right here, right? One way to find the center of a circle when given an arc is to fold it so that the 2 parts of the arc coincide. If you fold AB just so perfectly A lies on B, what is the relationship between the resulting crease and the chord AB? So what happens? That would make it a perpendicular bisector. So the crease is perpendicular to AB and bisects AB. So it cuts AB in half because remember, this is you fold it, so it's a mirror image, right? So that means the right side and left side are exactly the same, and it makes 90-degree angles because this is a fold that's exactly in half. You see that the fold is perpendicular to your line there, okay? The tree fragment 10.1, it was an arc between points A and B. However, the missing part of the tree formed a larger arc of the tree. Keen in a larger arc to distinguish it from AB. Well, the larger arc, the missing part, larger arc, how do you name it this way, right? How do you go around this way to name it so that people know you're talking about the bigger one? You can't just call it AB because people think you're talking about this one. So normally we put another letter in. So then a larger arc, we would call it arc ACB. Or another way to make it easier for us, it's ACB with an arc on top. That's how you name the larger arc. So there's a minor arc and a major arc. Minor arc is small, major arc is big. Okay? All right, moving on. In 10.1, the tree fragment formed the shorter arc between the two endpoints. The shorter arc between A, B points is called minor arc. It's written as AB like so. The larger arc is called a major arc, using 3 points, ACB, and you put a little arc on top. All right. What do you know about AB if the minor and major arc are the same length? Well, if the major arc and minor arc are the same, so the two arcs are exactly the same, then the AB is exactly halfway through the circle. So that means that AB must be a diameter. So AB is a diameter. Okay. Continue. In 10.1, folding an arc several times resulting in a point that seemed to be the center of a circle. But how can you prove that a line bisecting an arc or a chord will pass through the center? To consider this, first assume that the perpendicular bisector does not pass through the center. This is an example of proof by contradiction. We're gonna start by saying no, it doesn't work, and then you'll see that your proof is gonna eventually show you that no, the not working does not work. So not working, making it work. Okay. All right. So according to our assumption that the perpendicular bisector does not pass through the center, then center C will be off the line in the circle as shown to the right. So center is going to be on the side here, right? Now consider triangles ACD and BCD. Are these two triangles congruent? Why or why not? Well, let's see them. So ACD, right? ACD and BCD. Are they congruent? Why or why not? Well, let's think about it. That's a center, right? So that means this is a radius, AC is a radius, and CB is a radius. So they must be equal to each other. And this is a perpendicular bisector. So that means AB and BD must be equal to each other, right? And then the last piece here, let's see, we do have two sides. So it's a perpendicular bisector. So you have perpendicular here, you have perpendicular here. So this is a right triangle. So by hypotenuse leg, it tells us that the two triangles must be congruent. So then that means that center must be in the middle, right? So we have right triangles. So triangle ACD is congruent to triangle BCD by hypotenuse leg congruence. All right, and we showed that in our diagram, and that now we state it. Okay, so why does the part contradict the original assumption? Because then if that's true, then this leg must be the same. So in order for these two to be the same, the center must be on the line. Otherwise, as you can see in the diagram, it's lopsided, right? So, by CPCTC, we know that that side must be the same. It must be the same exact side. We can't have it tilted to the other side. I don't know how to say this right? So why the center must lie on the perpendicular bisector? So by CPCTC, the center must lie on the perpendicular bisector of AB. Okay. And again, there's also, these angles must be congruent. So that means the side must be the same. So again, it's pushing it so that the center must be on the perpendicular bisector. So we have two congruent triangles. Okay. All right. Last one, examine the chord WX in circle Z below. If WX equals 8, so this line here equals 8, and the radius of Z is 5, how far from the center is the chord? So how far from the center? So radius right here, if you can just connect any letter, doesn't have to be ZW, but it's any letter from the center to the outside, right? It's 5 units. How far is the center? When you're talking about distance, you're looking at this line right here with a perpendicular, right? So now, this is where it gets fun. You can take that picture out and look at just the right triangle there and write out all the information you know. This is 5, and because this is a perpendicular bisector, right? Because this line must go through the center like so, that 8 gets cut down to 4. So by Pythagorean theorem, by Pythagorean triple, this must be a 3. So the distance from the center to that chord, this distance right here must be 3. So the chord is 3 units from the center. Okay? In number 4 here, it says, what if you're given 2 non-parallel chords in a circle and nothing else? How can you use the chords to find the center of a circle? A. Determine how to find the center of each circle below, then use a compass to draw a circle that contains each given chord. B. Describe how to find the center of a circle without tracing paper. How would you find the center of the circle P with only a compass and a straight edge? So again, I think it's a little backwards. I would do finding the center and then do the A. But you could do this with tracing paper if you use patty paper. You simply fold your paper in half, the same way that we did with the arc, but you fold this in half, you get your perpendicular bisector. And same thing, you fold this in half, you get your perpendicular bisector is where they intersect. So that's where I'm gonna bring my compass in. I'm gonna find the perpendicular bisector. Remember, you start at the edge and go a little bit more than halfway, and you can make your beautiful fish on one side. Keep that same length. Notice I'm turning my paper and not my compass. It's a lot easier that way. So that is my very first perpendicular bisector. Grab my pencil, connect the two fishies, the fish tails. All right, so connect the 2 fish tails, and so I'm gonna connect that. There's 1 perpendicular bisector. The next one may be a little bit harder, but that's okay because it's a little smaller. Just make sure I'm more than halfway, okay? All right, so here's my first curve, and here is my second curve. All right, and I'm gonna take my ruler or straight edge. Remember, I'm not using it as a ruler, I'm using it as a straight edge. And I'm gonna connect, and notice that now this is my center. Where the 2 lines cross each other, that is the center, C. Okay, so now how can I do this? I take my center and I match it to one of the chords, one of the endpoints, doesn't matter which one. If you did this right, as long as it touches one, it should touch all. So notice how next I lean my compass and I turn my paper. If I turn my paper correctly, turn, 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 voila. See how the center allowed me to touch all, well, close enough. I'm a little bit off here, yeah, and that's because my pencil is not super sharp, so I'm just a tiny bit off. But again, I got these 2 endpoints, and this is close enough, right? I think maybe we're a little bit off. We can try again. Maybe I'll try it with these 2 chords. Match that chord. Okay, just a little bit smaller. A little bit of accuracy here. There you go. So there's my circle touching everybody. Okay. All right, we're gonna do the same thing here. Actually, try the same thing here and do it for circle Q. Okay. So circle Q, I'm gonna find my perpendicular bisector again. So turn my paper upside down. Here's my second line. All right. Here's my perpendicular bisector. There is my line right there. Okay, so there's my perpendicular bisector. Second chord is over here. My paper is totally upside down in whichever way, but whatever works, right? Here's my line. It may be good if you want to erase some of your lines, just because then you don't have so many lines going around. But if you can keep track of them, not a big deal. So I'm going to take this one and match it up to my perpendicular bisector. There we go. And this one may be a little harder to see, so let me see if I can figure it out. I see my line where they cross each other. It looks like the center is right about there. Okay, so same trick as before. Put my center down, match one of the edges. Oh, I think I got one of my chord edges. Okay, all right, ready. I lean and turn my paper. Turn. Oh, I think this one's better except my paper's stuck, but turn my paper. Aha, voila, so this one's perfect. Okay, that's how you find it with a compass. And straight edge, well, you know, I use my ruler, but anything straight like an index card. Okay.